Do we have it? Is the camera going to see me today? I miss the old camera. All right, I believe we are live. Moment here for Twitch.
I think you're showing the Twitch account. The Twitch screen.
I am showing the Twitch screen. At one point, we had to do that. See, I still don't know how to make picture go on screen. Things are happening over there. Boom. Do you see what I see? The answer is yes. All right, so it is the 19th of February. We are week 6 here at ASU, CSE 598. We just finished up file struct hijacking. I did end up adding a challenge, as some people noticed. It wasn't the challenge I wanted after you guys spoiled my fun, but hopefully for those that tackled it, it was at least a little bit interesting. So we're almost halfway through. We've got 2 weeks slated for kind of this Heap exploitation module. So we should be able to go at kind of a leisurely pace today and next week. And then we'll see what happens next. I'll announce that next week. We'll see what the shape of things look like. Memes. So if you started this module, the first 3 levels or so don't have this problem explicitly, but it still exists. This module is kind of all about these bins, right? These buckets of organization and how these, how chunks that are freed into the heap move around within these bins. And then playing around with this concept known as consolidation, which we'll take a look at. Now, this is a fair hit. All right. It's a very fair hit. I try and make short videos. I don't even know what do I do here? Is this the bins? The 54 bit?
Demo.
Okay.
I think you go through the different types of heap exploits that exist, or at least the strategy behind.
I don't watch my own videos, so
I watched half of it. So
okay. So hopefully it was 54 minutes of demo. So was it like somewhat useful? It's like I think about this as far as like future content. Is this acceptable? You can just say no, and I'm okay with it, right? Like these are attempts at shorter videos, and I'm clearly missing the mark somewhere. But if I don't go into like what I'm doing in a demo and like talk through it, then it just becomes I'm flashing code in front of you. Right? Yeah. And so that's a little bit hard to balance. I'll try and do better whenever I record new content here. This is not for the lap, but this was a solid meme, a solid relevant meme come out of 365. They don't even get extra credit for it. They're starting to mess around with reverse engineering and debugging and kind of looking at assembly, right? And so if you haven't done that, which hopefully the people in this class have, it does very much feel like if you have seen the show Severance, their task, you just stare at a bunch of numbers and then identify the ones that feel scary or feel weird. And when you're first learning assembly, it can feel like that. I thought it was fantastic. So I did launch a new challenge, as I said. Some of the blue belts tried to tackle it, and I took this as pain. It hurt when I saw this meme, but I'll share it. Okay, apparently it wasn't hard enough, and they're claiming that 365 has more difficult things than the 21st challenge that was launched for file structs. I'll strive to do better when I add challenging challenges. All right, with that, the rest of our time is demo, right? 5 slides, easy peasy. Have you guys taken a look at the pre-recorded stuff? We watched through most of it. Okay. No. All right. Almost there. So this module works a little bit differently. Let's go here to pwn.college than some of the prior ones, just from what you should do as a learner, as a user, right? If we looked at file structs, we kind of tell you what to do for a while, right? We say, hey, perform an arbitrary read. We say perform. So this is essentially perform an arbitrary write. You're trying to pass some check or set some value in memory. And we kind of build our way up here, right? We say use this primitive, use that primitive, go forth and conquer the binaries. When we look at the dynamic allocator exploitation, it starts off and it tells you what to do for the first 3 levels. They all say something to the effect of leverage consolidation to obtain the flag. And then you get to level 4 and you get the super helpful text. It says perform an advanced heap exploit to obtain the flag. You're like, I got it, right? Clearly we had a section where we talked about advanced heap exploits. And then you go to level 5 and it says do the same thing. And in fact, all of them for the rest of the module say this same extremely useful, right, help text.
Yeah, 365.
What's that?
We have 365 descriptions, and then we have this.
Yeah. So 365 does a bit more verbose descriptions. And that's because when you're first learning this stuff. Oh, thank you. Somebody on Twitch says that they thought 21 of file structs was reasonably hard. So like the goal was to foster learning, right? Not to just create this brutal grind. But this module does have a bit more of a brutal grind bend to it, right? From the challenge descriptions, so we don't really tell you what to do from level 4 on. And if you read the module description, it kind of gives you an idea of how to play this module or how to approach it. And what we're doing here is I'm not telling you what to do. Instead, I point you to this repository called How to Heap. And How to Heap is a collection of proof of concept exploits for a particular heap vulnerability. You're taking advantage of a specific thing that you can do that's kind of interesting in the heap. How to Heap has a ton of POCs or proof of concepts, and they're organized by libc version. So we want to know what version of libc are we working with. So let's fire up one of these. Oh, that one says Consolidation. I think they all use the same version of libc.
It's 2.3.
It's 235?
Should be. That's what the video
I
says.
would have guessed 231, but I trust VideoMe. Right? VideoMe knows these things. But it's kind of a trust but verify. So if we take a look at the challenge folder, okay. There we have a what did I do? I'd like to know if I had a major goof. We have the challenge. We have lib. And when we have a lib folder, that is typically what the challenge is linked against. So challenge lib libc. So we can run challenge lib libc. It turns out past me was correct. You guys listen to him. That was a good idea. It is libc 2.35. So this should be easy, right? We go into here to glibc 2.35 and we get this list of POCs, right? How does that help me with level 4? Well, if I run level 4 here, it says I can manage 16 allocations. I can call malloc, safe read, free, puts, send flag, and quits. We could run some of these. These should be.
I don't think you know.
Oh, I want send flag. Send flag. And it says I'm not authenticated, right? And so I have to do something similar to what we had with the file struct module, or what primitive do I probably want? This thing says I'm not authenticated, right? If we were to open this thing up in Ghidra, or why Ghidra? We could open it up in Ghidra, but if we were to open this up in Ghidra or IDA, we'd probably see, we can do that. That there is some value in the BSS, more than likely, but take a look at how this flag function works. So I'm interested in send flag. See if we can find her here. Got malloc. Got free. I've got puts, safe read, send flag. Send flag just checks if this authenticated value is set. If it is, it'll open the flag and then write it out to standard out. So where is this authenticated value? IDA tells us here that it's in the BSS. So there's some memory location that I need to do what? I need to read it. I need to write, right? I need an arbitrary write. And the idea behind this module's design, for better or worse, is you look at the challenge, you identify what is the primitive that I need, right? I need an arbitrary write. And then you identify what are the constraints of the challenge. And when I say the constraints of the challenge, it's, okay, I want to malloc something. Okay, I picked size 40. The challenge tells me, no, you can't do that. The smallest thing that you can malloc for this challenge is BB8 or hex BB8. Is BB8 intentional? Probably. Like it's not completely random.
No, it's a reference from Star Wars.
Oh no, it wasn't. It wasn't a Star Wars reference. I'm not that clever. I appreciated that you think I am though. And so we're restricted in the size of the allocation we create, right? Now, I haven't talked about the bins yet for those that didn't watch the pre-recorded, but I'll get there. If we take a quick look, let's do it in, let's look at it in GDB. We'll go off script. We go off script every time. Well, PSAUX, grep challenge, sudo GDB A221. All right, I'm in the challenge. And one of the things that we did in first, did I lose that? CP. I'll run this guy instead of challenge. See, X, grep, heap, attach GDB to this guy. Okay. When we used Jeff or the challenge not showing it, I will look into immediately after class.
Okay.
It's going to be a libc thing, and I will probably provide you some magic to fix it. It's going to be a dojo. Dojo is. But if I look at a normal looking binary here, and we run heap bins or the equivalent thing in pwn debug, in the past we always looked at the tcache, which it does it show the tcache in? It does not. It says uninitialized tcache because we haven't put anything there. And the only line that we looked at in the prior modules was whatever was right here for tcache. We just ignored everything else down here. Well, it turns out, in addition to the tcache, there are a series of bins. So we have, for instance, fast bins, unsorted bins, small bins, large bins. And there are rules, as you can probably infer from the name small bin and large bin, on where these chunks go based upon the size. And so this limitation that the challenge is giving you in level 4 of BB8, it means that I can only allocate things that are, I'm going to say, large, right? And so we should note that. And if you watch the pre-recorded lecture videos on the bins, there are slides, and I will probably be referencing them as we move through the demo here. The slides tell you what are the requirements for a specific bin. So if I get to, for instance, small bins is anything of a constant size up to hex 1024 bytes, right? Those size chunks can end up in this small bins functionality. Things that are larger than that can end up in the aptly named large bins. And so that's where anything larger than the small bins ends up. Now, this can sound all confusing now, sort of like what is an unsorted bin and a large bin. The demo will make some allocations and see how these things flow through it. But the kind of way of approaching the module is think about what primitive you need. So I know I need an arbitrary right. Think about what bins you can interact with based upon what the challenge is restricting you to do. With that knowledge, go over here to how to heap glibc 2.35 and look at these things. So this is a POC of a specific exploit. And we could get this onto the dojo, compile it, and run it, and it's going to show us what goes on the heap with some printouts to create an arbitrary read or to create an arbitrary write. And it's not going to make a ton of sense. As you can see, there's quite a bit going on here, right? And this is all written in C. Now, if I were to just compile this and run this, it will prove that the heap vulnerability exists. But that doesn't help me on the actual challenge because I'm not interacting with C here, right? I'm interacting with these commands that I then have to automate with pwn tools. And so what we need to do is we need to look at and understand a POC, determine what bin does this interact with. Does this POC use large allocations? Well, right now it's the first thing it says it's doing is it's allocating a small chunk and it is, or allocating a victim chunk that says its size hex 100. Can I allocate something of hex 100 in this challenge? No, it must be larger than BB8. Now, does that mean that this POC doesn't apply here? Maybe. It doesn't matter if this is hex 100. I don't know. We'd have to read the POC and understand what it's doing. Now, some of these things, like it says here, allocating dummy chunks for using up the tcache later. You may not know what that means now. We can take a look at it. So I have this dummy binary that is our example. This guy here, heap example. It has no restrictions on what I malloc or free, right? It works very similar to these challenges. I compile it from the same source. And we're going to use this as kind of a straw man to explore the bins and see how we can put things in it, how they move around, and see it in GDB. And so I plan on spending the rest of the time with this heap example so that we gain an understanding of how the heap works. But in order to succeed in the challenges from level, where am I? Level 4 on, we want to be thinking about what capabilities do I have? I'll map that to our understanding of the heap that hopefully we gain a bit today. And then apply that to these POCs. And every single one of these is a different technique that exploits different functionality between these bins and how memory is laid out. For every challenge that is on here, there is a specific write-up or POC that was kind of the inspiration for it. So I looked at the POC and then built the challenge with that in mind to restrict it to hopefully there's only one that is the correct approach for it. Okay. So now that I got that out of the way, a great disclaimer. Let's change this up just a little bit. Let's have a do.py. I need a new do.py. You love to see it. And let's start thinking about these bins and what goes on here. So use bin n python 3 from pwn import star context arch AMD 64. Get our boilerplate there. Our binary today is heap demo. It's just heap example. There we go. We can take a quick look at this guy. Just so we are all on the same page as far as functionality. I think for the most part, it does what it says on the can. So we have an infinite loop where we're going to take a series of commands. If we quit, it turns out we break and quit. If we get malloc, we get to pass in an index number. This index number needs to be any number between 0 and 15. That's going to determine a slot right here in this alloc struct. Now, IDA is not going to do me justice here on this alloc struct, and I don't want to make a struct in IDA. But we just from looking at this right here, what can we infer about what is going on with this alloc struct? Like we've kind of seen this pattern in the past. It is a series of, I'm going to call malloc, and we're going to store the results of that at some offset of this alloc struct. So there is probably an array of
16.
What does malloc return? There's 16. There's 16 what? Yeah, 16 addresses, 16 pointers stored at part of this struct. And we see that this struct is located on the BSS. So just so we have kind of a working model of what's going on. We don't know what's going on with these first 32 bytes, right? That's some offset into the alloc struct before these pointers are stored. We don't know what's going on there yet. Oh, yeah, we do. Well, no, I don't know what's going on at 32, but I see something else here. And so within this alloc struct, I don't know what's going on with the first 32 bytes, but I do get to see that the size, which is the size of the allocation, is also stored at an offset into the struct. So the struct has a series of pointers that are returned by malloc, and then it is also holding these sizes. And so we have within the struct something for the first 32 bytes, a series of hopefully 16 pointers, and then 16 pointers would be what? 8 times 9 is 90. Is that right? See if I can math. 8 times 16 is. Oh, that's treating as a D word. That's why this math is off. Itemist. Okay. But we have an array of pointers, and then after that is an array of D words that are probably against the size. We have the option to see alloc. Now, this was one of the things I was asked on the Discord. Is like, what is this thing, and why do I care about it? Anyone want to know where to find the answer to that? You do know. You do know. All right. It is the one thing that I say all the time. You just don't want to say it to spite me. The answer, as always, is the man pages, right? And so if we man malloc or even calloc here, we get the man page for all of this. If we were to take a look, which I believe is what the person on the Discord did, because they essentially regurgitated exactly what the man page said, which is a good thing. That means that they knew the answer to their question. They found the info. They just weren't confident about it. And what we see here is calloc is a function that allocates memory for an array of n mem elements of size bytes. So this follows a similar pattern to like what we saw with the IO stream. We go up here and look at the function signature for it. It doesn't just take a size like malloc does. Instead, it takes how many things do you want, and then what is the size of the thing. Internally, it is multiplying these two to determine what is the size of the allocation. So that's one thing that's different. It also says that this memory is going to be allocated to 0. We don't have that guarantee with malloc. Right? Where calloc does give us this guarantee that these are zeroed bytes. It also, let's see. Okay, so it doesn't say it in the man page. So you must have gone a little bit deeper because there was something about the tcache that was said. Okay.
It was from how to heap shellfish.
Oh, shellfish how to heap tells us something good. What did we learn there? Where did we learn this?
House of I think it was fast bin consolidate.
Okay.
I think
So we started the journey here. And we see in the comments, it says using calloc here doesn't take from the tcache because calloc calls something, something, something. About to die. Okay. So calloc, the man page tells us that it gives us guaranteed zero memory. Do we have that guarantee about stuff that's in the tcache? No. We don't. Right? We played around with the tcache before. The tcache does specific things for like the first 16 bytes, but everything after that, does that get zeroed in the normal operation of the tcache? No, we just let bytes be bytes. And so it would be, I would say, not performant to regularly zero out allocations from the tcache if it's not necessary. Instead, this will give you a fresh region of memory that is guaranteed to be null, so it won't pull from the tcache. And that is a useful thing when we start thinking about the heap. So that's why calloc exists here. The tcache is going to be like this constant problem for us as we try and interact with things deeper in the heap. Okay, I can call free, and calloc just takes an index and a size, and then it is going to do that same thing that malloc does, except now we're saying that we want, I don't know, consult the man page. Is that one member of size, or is that members of one? One member of size is what it is going to request here, right? But it's still putting the pointer into this array, and it stores the size. I can call free. Again, I specify an index. We're going to call free on whatever pointer it was that was stored there. I can call puts. So I can print whatever is in an allocation. I have this interestingly named function, safe read. Safe read is, of course, perfectly safe at all times. And safe read is going to take an index, verify that it is less than or equal to 15. It's then going to access the pointer or the size, access the size from the alloc struct that corresponds to that index. And then it is going to read into memory. We're calling read, so we're reading from standard in to the allocation of whatever the size is that we store. Okay. And it looks like we're going to puts. Probably a string. No, I'm a liar. I'm going to print something off, but not particularly interesting, right? There's no bait and switch here. Everything kind of does what it says. Read flag, we already. No, this is a different read flag. This is my example. So read flag is going to apparently loop for 0 times and call malloc. So it's going to malloc and then read the flag into the buffer. Do I get to control this V8? Or is this V8 just happening? This V8 is just. Give me. Okay, so V8 is some constant here. 15, 12. And that's it. Any questions about what the binary itself does? Cruising. All right, so let's start scripting this thing. The first bin that I think is worth talking about is the fast bin. And I believe it's the first one that is presented up here. And that's for a reason. So if we recall the tcache on this table here, what does the T in tcache stand for? Thread, right? It's a thread local cache of small allocations. Well, the tcache has a maximum size, and this maximum size is 7. So what happens when I free 8 things that could go into the tcache? Well, let's do that. I'm going to automate this. So we're going to malloc. Let's do a size 8.
Do you know that?
I'm sorry. Do I know what an F string is? Not today. But I know I can type colon pound equals and get stuff to print in hex, and that is pure magic. So we're going to malloc 8 things, and then I'm going to free 8 things, and then we will just p interactive.
You don't need the size.
You say I don't need the size of 8.
No, for free.
Okay. And then let's GDB debug this. So now we run my do.py. It turns out I should probably use send line because this is calling scanf, and that would turn into a whole bunch of garbage. Okay. And we see the challenge did whatever it did, right? And what I'm interested in is what is the state of the heap. And so in GDB here with Jeff, we'll heap bins. And we see that we now have tcache entries like we've seen it earlier. The tcache is a singly linked list. This is the first entry in the list. Every chunk in a singly linked list has a next pointer. Since this is telling me where a chunk is, just as a quick refresh, I should be able to examine the address or examine the bytes that are at the beginning of this first chunk. This should give me the address of the next chunk. Does it? Where am I? This chunk 6340. Why does that not look the same? Because of mangling, because of safe linking, right? But do you believe me that that's the point? All right. And so we've seen this before, and it turns out the max size for any tcache bin is 7. So when I freed this 8 chunk, this list is full. And so it gets freed into the next thing deeper into the heap. The initial entry point here is the fast bins. The fast bins works basically the exact same way as the tcache. It's a singly linked list, except it is unlimited in size. Now, it is also a caching layer, right? The intuition here is the tcache is a caching layer for every individual thread, right? But there could be patterns of access across threads for the entire heap, right? Maybe this long-running server program is going to keep allocating things of size 20, and so we want to keep them on hand. And if we look at the flags value for things in the tcache, remember this in use bit? So things in the tcache are considered in use. This is a lie, and we'll see what this lie means when we get down into these later bits. And if we look at fast bins, it also says that this chunk is, or the previous is in use, which is again a lie. And that's because these are both caching layers. These caching layers are simple linked lists that lie to everything deeper in the heap. Now, the next bin that is interesting is the unsorted bin. The unsorted bin, as the name kind of implies, is where everything that we haven't sorted goes. The fast bins is a caching layer for the heap that is shared across threads, but is still only for small-ish allocations. It has a similar size limit as the tcache. If I want to get something into the unsorted bins, I can do this same thing. This fill tcache +1, or this is malloc 8. We malloc 8, and when we free 8, this is going to fill the tcache +1, and because it's small, it goes to the fast bins. If we do the same thing, but with a bigger allocation size, I don't know these off the top of my head, so I'm going to go with hex 1000, something reasonably large. We run the same thing. Okay, we get nothing. Now, this is because of an optimization. You remember when Jan was ranting about the wilderness?
Some videos.
It's on some videos somewhere. Jan said the wilderness.
Yeah.
Not sure binary understands hex. Oh, did I? Okay, that makes sense. Good call. Good call. Thank you, Twitch. Okay. Now we see that I have put something in the unsorted bin because this chunk size of hex 1000, which is 4096, is too big to go in this fast bins area, right? And so we freed it. And the question right now that the heap kind of has to ask is, does it make sense from a performance standpoint to figure out if this is a big thing or a small thing right now? The answer, you just freed it. The heap's just like, whatever, we'll just throw it in this pile and deal with it later. Again, it's performance optimization for chunks that are bigger than the fast bin. Now you'll notice something else occurred here. The fast bin is gone. So there are rules, and this is a heuristic rule. I didn't intentionally trigger this, and I'd have to refer to my own slides to know exactly where the cutoff is. The fast bins occasionally gets clear. I happened, instead of saying over, I guess it should say equal. The fast bins occasionally gets cleared out. The whole reason that we're doing all of this weird stuff here is to prevent something called fragmentation. Does everyone know what fragmentation is? If I say memory is fragmented? Because if I had a bunch of if I hung on to all of these small fast bin things, I would have a whole bunch of these like hex 20 chunks just kind of hanging out. But what if I never need something small like hex 20 again? If a large allocation occurs, the fast bins will get cleared out in an effort to try and satisfy the malloc request that came in. Now, what'll be interesting to see here. Oh, this doesn't print out pointers. Let me change something real quick. I need walk through. You're seeing behind the curtain now. Sure, I did. What I think I did here. There. So now you get help text. That's how we can generate challenges automatically. Pwn.shop is open source. You can see it at github.com/pwn.college, Pwn.shop. It's scary. But yeah, this is how we generate challenges. So now I have the same challenge, but I have this help text output. Now, what I wanted to show here, so I run my do.py. We let this thing run. Now that we have help text, my claim is we cleared out the fast bins as an optimization, right? We said we don't want these anymore because what the heap's going to try and do is it's going to try and reuse this space because I'm asking for something that's large. And so the chunk that was in the fast bins should be like 8, this guy right here, which was 1B55380. Now, when I malloc something large, what did I get? 1B55380. So what happened here? I'm getting the same chunk. I malloced a chunk of size 8, and I got this address down here. But then when I malloc something large, I'm getting that same pointer. How is that possible? This was an 8-byte chunk, and now it's a 49 or 4096 byte allocation that I'm getting.
Consolidation.
Right, consolidation. So the whole reason that we jump through these hoops of these bins and have all of these rules on why things move around and why things get cleared out is to try and prevent fragmentation and consolidate chunks, which means to take the little pieces and smash them together. Now we can visually see this. Where did that get consolidated with?
First fast bin.
So well, that is the same address that got returned. Up here, I called Allocate, and I got this. Let's just look at it in GDB. We will check fast bins. So we'll block our challenge here. Okay, so it's check fast bin, and if I heap bins, we see that we have filled the tcache, and the 8th chunk is now in the fast bin. That happens to be chunk size X1. What is after this? I'm going to say physically, but it's really about virtual memory. If we type heap chunks, I get this. pwn.debug has, generally speaking, people like the pwn.debug version of this more than Jeff. I'm fine with Jeff. But what this is showing me is where are these chunks located in virtual memory? If we look at the virtual memory addresses, these all move in increasing order. And the chunk that is in the fast bin is F05380. and we see that it is the largest, or not the largest, the last chunk that is in that region. Remember, that is the heap. So we can think of it. It's not entirely true that this is the beginning of the heap, and then this is the end of the usable heap. And what is this last giant chunk here? I didn't make this. The wilderness, right? The wilderness is this giant chunk that is everything that isn't currently being used. And so right now, in memory, there's this chunk that is in the fast bins. And when I hit enter in the Python code here, it's now going to start mallocing 9 things of size 4096, and then free them. The act of doing that first malloc, is going to cause us to declare all of the chunks that are in the fast bin as free and available, and we need to consolidate them. Where does this consolidate to? How do we think about consolidation? Consolidation is when we take 2 chunks that are free, that are not in use, and we smash them together. In order to smash them together, they have to be located right next to each other.
Just I'm gonna grab from the tcache. Just gonna look into the fast bins. And since we only have one allocation there, it'll take that and start the address from there. So I start the allocation from the address, and then give it hex size 4096 or
Okay, so the statement was, it's not going to go from the tcache because I'm asking for something that's too big for the tcache. Now, the phrasing on the next part is quasi-right. It's ultimately what happens. It's not necessarily the order of operations. When you ask for something really big, we're not going to check the tcache. It's bigger than what the fast bins can offer. And when we know we're going to try and obtain an allocation that is larger than the fast bins, we immediately say, clear out the fast bins, treat them as free usable space because we're looking for something big. We don't want to have a bunch of small guys. The act of doing that will mark this allocation, which is the chunk that is in the fast bin that currently is marked as in use. We don't know that it's in use from here. We know that it's in use from here, because the flag for is this chunk in use is obtained by the next chunk's previous in use bit, just for clarity. Okay, so if we mark this guy as free, where can it consolidate? We think of it as you either consolidate backwards or you consolidate forwards. Well, if we consider the backwards consolidation case, it would try and take this free chunk and combine it with this right here. Can we do that? No.
No,
Why?
because it will get consolidated with the wilderness.
So it could. It will ultimately get consolidated with the wilderness. But why does it not go backwards?
that's the previous in use flag of the one previous. That last one in the tcache has its flag set, so it won't consolidate with.
Okay. So the chunk that is, again, I use the term physically, but it's not accurate, right? I think of it that way. That physically precedes it is in use. We know that because the chunk that is trying to backwards consolidate has its previous in use set. This makes sense because where is the chunk that is at address 5360? If we were to scroll just a little bit up there, it's the first chunk at the head of the tcache. And the tcache, remember, is a lie. Everything in the tcache, it's in use for our consolidation purposes. The tcache is all a giant lie. And so when we flush this out, this guy is suddenly a free agent to consolidate. And as was mentioned, it consolidates with the wilderness, which creates one big chunk. Once we have this one big chunk, right, it just is absorbed into the wilderness. The question is, can I satisfy this 4096 byte ask that malloc had? And the only way, since right now our other bins are unused, is we just pull it from the edge of the wilderness, and the wilderness starts at where that happened to be. Now, one of the things that was said that I can immediately, yeah, I'd have to do this. I lost my GDB. Conks. One of the things that was said was like this has to go forward into the wilderness. Is there a way? So this is just thinking about Heap and just what we've said right now about consolidation. Is there a way I can prevent this from consolidating?
There is.
There is a way. I should start asking questions for there is. Did you know what that way is?
I know there's a term called a heap guard or a
Guard check.
guard check. Yeah.
Okay. Is that a shellfish term or is that a me term? I call them guard allocations. There probably is a correct term for it. But I can prevent this from consolidating forward with the heap if I have something that is in use that's in front of it, right? What would I need to do in my little script here if I want to protect this 8th allocation from the wilderness? What do I need to do?
Just have a malloc after it and don't free it.
Just put a malloc after it?
And don't free it.
And don't free it. Okay. So I send line malloc. What are we at? I don't know. Let's use 15. Hey, happy with that? So I am here, but I haven't done my large allocation yet, right? Because I'm here at check fast bins. So all I've done is I've malloc 8 times these small things I've created by guard allocation, and then I've freed the first 8. Right, so we're at that kind of same state. If I continue onward and set the exploit script free, or our toy script here, we take a look at the bins. What have we done? We've moved that small allocation into the small bins. We've accidentally discovered what this next bin is, right? The small bins is where things go after they have, well, actually, there's a number of items instead of a curry. How did I get?
Oh, I think you malloc 9 things and
What else did I do? Oh, yeah, I put something large in there at the end. That's why. Yeah, I meant from these malloc things. That's how I got the unsorted entry. So when we cleared out the fast bins, it went to the unsorted bin, is what happened to it. But then we tried to use the unsorted bin. And this is kind of a difficult thing to show for this particular scenario because I'm going from the fast bin to the unsorted bin. But when I clear out the fast bin, things end up in the unsorted bin. The unsorted bin, as the name kind of implies, is where big things, small things, everything that we just don't want to deal with, and it's not a cached, it's not a fast cached free chunk. Everything just goes in here. The logic here with the unsorted bin is before we file it away, the heap might ask for something of the same size, right? It's not small enough to keep in the tcache. It's not small enough to keep in the fast bins, but maybe you could envision an application that is going to malloc and free, I don't know, some user struct. And this user struct is 4096 bytes in size. Instead of filing it away where we now have to do this like lookup thing, We just say this was the unsorted bin is this pile of stuff that you freed recently. And so when we try and malloc something, if we wasn't in the cache and if it wasn't something that could be satisfied by the tcache, and it wasn't something that could be satisfied by the fast bins because it's large, the next place that a malloc will look is this unsorted bin. And it is looking for any chunk that can satisfy what you're asking for. So it's just this pile of stuff that we grab the thing on the top of the pile and say, hey, is this good enough for what you're looking for? If it's not, we file it away at that moment, right? If it is, then we just stop and we say, here's something that's good enough for you right now. And we leave the pile alone. So it's an optimization on whether or not we have to sort it as small or large and do whatever bookkeeping is necessary down here. If we grabbed something from these unsorted bins and it did not satisfy the constraint, which is what happened here with our small allocation. We had our 8th thing from the tcache that we freed. It was chilling in this optimization layer. We flushed out the fast bins because I made a large allocation, which then sent it to the unsorted bins. Then we were digging through the unsorted bins to be like, hey, is there something in the unsorted bins that can satisfy my 4096 request? The answer was no, because this was a 20 hex 20 byte thing that was chilling in the unsorted bins. We said, all right, this is small. We threw it in the small bins and now it's down here. And this is where it'll live probably for the rest of the time, right? Because at this point we have there's a lot of layers in between actually accessing this chunk, right? The same thing happens with the large bins, except it just needs to be, as the name implies, a large chunk. So if we freed all of our large guys, right now this is in the unsorted bin, right? When did I say we clear out the unsorted bin? The unsorted bin is a pile of stuff that has been freed that the heap's just like, I'll deal with it later next time you ask me for something. Like I think of it like a pile of kids' toys. Like I think of Toy Story or whatever. Right? There's just this pile of chunks, and we're just like, yeah, all right, you gave it to me, you freed it. It's not going to go in this caching layer, and so we just throw it on this unsorted bin. Right? We just throw it in a pile. The unsorted bin gets cleared out when we malloc, when we ask for something. So if I want to move this chunk into the large bins, I need to malloc something. Now, if I malloc something small, like if I malloc something that's, say I try and malloc hex, I don't know, 8,000. What's it going to return me? Any guess? What pointer are the heap giving? I can pretty confidently say, we'll see if I'm master of the heap today. What address from right here the heap will give me if I were to append a malloc 4096?
Is it the one that ends in 3C0?
Okay. The signal is it this one here ending in 3C0? My prediction is yes. Why did you think that?
It's like the next viable one with enough memory.
Yeah, it's the next viable thing that has memory with our kind of order of operations of what bin, what bucket are we looking for, right? If I try and malloc something that's 4096, can it come from the tcache? No, the allocation is too big. Can it come from the fast bins? I don't think so, because it's too big. So where's the next place that the heap is going to look for? It's going to be like, here's the pile of toys, right? Let's see if one of them fits. I should have just continued and done it with interactive. Let's do that. Boom. Okay, so our claim was if I malloc 4096, I'm going to get this 3C0 pointer. That's cool. I'm just going to go with it. We'll malloc into, I don't think I've used slot 10. We said 4096. Look, we got that address. And so there's a lot of moving parts here. And one of the things that we talked about with the tcache is that when we talk about the heap, is that the heap is in fact deterministic, right? When we were talking about the tcache, our mental model of like what address am I going to get was just this singly linked list. It's going to give me whatever is at the head of the list, and it's kind of nice and easy. But when we start thinking about larger allocations or things other than the tcache, we now have to have a mental model of, well, what does the heap do? Where do these chunks come from? That is the stale example. What's interesting here is we got our 3C0, right? What is this guy?
What's left?
Right. We just picked up the thing that was on the top of the pile. We snapped off our piece and said, here you go. We'll deal with the rest later next time you ask me for something. Now, based on kind of what I've described here, how do you think I could move this trunk from the unsorted bin to the large bin? Do I have the large bin? Yeah, the large bin. We haven't touched that yet there. I haven't told you, but what do you think would be the answer?
I would, so I have a doubt regarding just the unsorted bins.
I'm sorry?
Just the, I have a doubt regarding just the,
You have a doubt regarding the unsorted bins. Okay.
so let's say you keep on taking away from the unsorted bins.
Okay.
Uh,
What do you want me to do? Let's do it. Let's see it live. What are we
so,
thinking?
Let's say, like this time, since you removed 0x1000,
Mhm.
0x7070 was still left. So
Mhm.
that's big enough to be kept in the unsorted bins. But what if the memory remaining is way too small to keep in unsorted bins?
So the unsorted bins doesn't care about the size of the leftovers, as far as I'm aware. But we can find out let's do it for real. So let's make a remaining chunk of like hex 10.
Yeah.
That seems reasonable. I need to let Python guide me on math. So we said what, hex 7070 left? What's in our unsorted bin? So I want to know what is the decimal of hex 7060. Yeah. So let's malloc that much. Continue down here. Malloc. I don't think I've used 11. I'm running out of slots. All right. And you want 28768. Okay. We did it. Ooh, it's gone. Oh, did I go?
Oh, it might.
Yeah. I went too close. I should have kept a little bit more. We're going to refire that. Do you understand why we both had this moment?
Yeah, because
So
the
there-
metadata that's
Yeah. There's a difference between the size of the chunk and the size of the allocation. And I picked something that was so close to the size of the allocation that it would return that size chunk anyways. Yeah. So I need to give it a bit more space. So let's do it live. It's a good question. I think it would hang out still in the unsorted bin, but it's a good question. Okay. Malloc. This time, let's sanity check ourselves because I didn't do the. I didn't steal the size, so it's hex 80.
maybe
Is that a reasonable number?
just take another 20, so 70.
You want that?
No, take away another 20, so 70 E0 or E0.
70 E0. You want that?
Yeah.
Is that a good number? You like that number? All right. It's like the meme said, man. You look at these numbers, and if they feel scary, right? Okay. We continue. We got that. We'll get back here. We'll heap bins. And okay, so that's still too big. Let's go a little bit. We didn't break off something big enough. You want just F00?
Yeah.
Okay. 3840. Now look, 11, 38, 40. Okay.
Yes.
And it's still there, right? The algorithm for the unsorted bin really is just this like pile of, I'm glad my mental model works. This pile of like discarded toy, but we're just gonna like grab it and break off a piece if we can. And so the fact that it is so small doesn't matter because it's the result of breaking the pieces off to satisfy whatever was immediately.
I think it makes more sense to say you're grabbing slices of cake, man.
You like slicing the cake? I'm over here destroying dolls and toys. Yeah, all right. It's probably cake is probably a better analogy here. Now I do see let's see, what time did we start?
30-ish.
And it's a little bit after 5:30. All right, let's take 5 now. It's been about an hour. I'll pause the stream here. Everyone can have a bio break. we have returned. It turns out what we just did here is creating a specific size chunk in the unsorted bins is actually useful information if you're tackling the first few challenges we learned. So it's not a completely useless rant. But where I kind of left us was how do I get things into this large bin? Since we had our little experiment, which I think was cool, to see if we could put something small, I'm going to restart the challenge so that we have something big in the unsorted bins. All right, let's verify our state. So we're back to having this giant chunk here in the unsorted bins. What do you think is our strategy to move this thing or get the heap to move this thing from the unsorted bins into the large bins?
I think magic more than X88.
All right, the statement was malloc something more than hex 8080. Let's see if we can do that. You want 40,000? Turns out you guessed right. And we see now that same chunk that was in the unsorted bins. What happened? The heap grabbed the piece of cake and tried to slice off a piece, except it turns out the piece that we wanted was too large. So while we were holding on to that, we said we're going to put it in its respective bin. Does anyone have any questions about how stuff moves through these bins? The next thing that I'm going to pivot to is how they actually work. Because the tcache was our nice singly linked list where we had a head pointer to a chunk that points to a chunk that points to a chunk, right? It turns out that not all of these work that way.
We never got the allocation guard.
We never got the allocation guard thing.
Like,
Well, what are you after?
we never did a allocation where a free chunk in the fast bins would stay there.
Well, or a free chunk in the fast bins.
So it doesn't consolidate like at least the top chunk of the fast bins because we didn't.
Oh, so no, we did. That's how we got something in the small bins. So it wouldn't stay in. I lost it. Boop. We still
right. I see.
We had something that was in the fast bins, right? And then I did the big allocations, right? And when I did the big allocations, when we try and get something big, it's time to stop capping in the fast bins. So we move all of the things from the fast bins to the unsorted bins and try and consolidate them together, right? If there was a guard allocation, right? If the thing in front of it and the thing behind it, and when I say thing, because thing is like the greatest descriptor, right? What I'm really saying is if the
380.
if the chunk, right, this guy or this guy's
380 is what we were trying to guard. So 380 was never free.
380, I'm not.
It's
This one, yeah.
So that's in the small bins.
So now it's in the small bins, right? And it's in the small bins because we had a guard allocation in front.
Which is the 380.
Because this is in use, which means these two can't combine, right? Except at the time that it was freed, it was this guy, the guard allocation, and then the wilderness, right? The rest of this is the result of the large bit stuff that we did.
So is it possible to not move that to the small bins? Is it possible to keep that fast bin chunk in the fast bin with a guard, or is it because we are allocated
So
big
the-
that's going to the small bins?
The question for Twitch, tell me if I got it wrong here, was, is it possible to keep this in the fast bins? And if we were to consult the grand rules here for the fast bins, there is a slide that says clearing and consolidating the fast bins. It's whenever something, it says over, it technically should say equal or over based on what we've done, right? We've proven. But if there is a mallet that is 1024 or larger, then we flush out the fast bins. That just happens. So I could keep it in the fast bin as long as every future allocation is smaller than 1024.
Yeah.
Right. Because the fast bins, we think of it like the tcache, except we don't hang on to it forever. It's a caching layer for all threads, right? If you exhaust your tcache, we go to the caching layer that is the fast bins. All right, we go tcache, and then the next place that would be checked to pull something from on mallet. The tcache is going to be thread local, so that's going to be your fastest caching layer. And then if we can't pull from our thread local cache, then we're going to try and access the fast bin, which hopefully is a caching layer for everyone else on it. Now, since this is a caching layer for all threads, we have this like race issue there, right? We have contention. Like if we didn't have the tcache and we had multi-threaded things all trying to access the fast bins, that is actually slow because we have to make sure that each thread kind of owns the fast bins when we return a pointer from it, right? And that's why we have the tcache layer in front of it. So in multi-threaded processes, each thread has its own cache to hopefully prevent contention on the fast bins, which is a shared common caching layer.
So why is the tcache only 7?
Why is the tcache only 7? I don't know. I would guess, and this is definitely a guess, that it is a heuristic number. So if and you'll find that is the case for a number of things, and they're all subject to change as far as like where some of these values are chosen, right? So like the fast bins, the general way that you flush out the fast bins is that you commonly see is this like large allocation 1024, right?
Just like a page.
I don't math, man. I don't think that's a page, is it?
No, it's not.
Pages 49.
Print the decimal version of X 1000. It is not a page. It's a fourth of a page. Why a fourth of a page? I don't know. Someone smarter than me that did a whole lot of performance metrics, right? Decided that was going to be the number. But there's also like this other weird scenario. If a chunk that is around 65 kilobytes in size happens to be free, I don't know, right? And you have to look at the libc source, and it's just going to be like, this was chosen heuristically because sometimes this happens, and then that is enough to trigger some behavior.
If you free a big chunk, it'll also clear the fast bins.
Right? Because then it's going to try and smash stuff next to it. And I mean, one could kind of reason that if I free something really big, I'm working with big things, big allocations, which means I probably don't want small things being fragmented because I'm working with big data. Both of these are indicators of I'm working with large allocations, in which case I probably want to defragment anything before I try and obtain another large allocation. And these values and cutoffs are subject to change based upon libc, which I think I already mentioned. Okay, so we got to see how we could prevent consolidation. I think this is a fine opportunity just because I'm looking at it now before we go into pointer length. Can I force consolidation here? So I have this, let's see. I have this chunk right here, right? This little dinky hex 20 guy. And that is chilling right now in the small bins. And if we look at heap chunks,
I think you're on the one above it.
am I
That's
failing?
3A0.
3A0, what am I doing?
You're looking at the malloc one, not the free.
Oh, okay. Yeah, I was like, this should be free. And I was like, why am I, thank you. Okay. So we have more than one hex 20. Oh. Okay, so this one is not in use. The 380 is not in use because the chunk that is physically after it does not have the previous in use set. What if I wanted to create a hex 40 chunk? Can I do that? Can I cause this to happen?
Starting at 380.
Sure. Can I do that? I want to make a chunk of size hex 40 to exist in the heap, starting at this address 4380. Let's see if we can do that. What do you think?
Wouldn't you have to free the alloc chunk?
I need to free one.
The chunk with the address 380.
Okay, so the statement was, well, we could just free this guy because he's in, the 380 is in front of it, and 380 is not in use. So let's see if we can free 380. Do I own that? What is my number? 380. Where are you living?
It's at malloc, so it's not going to be the bit.
Previous use. Oh,
Yeah, you might want
I need to,
to
yeah,
index in the actual challenge line. Chunk it
up
up
here. 380. Okay, so it is
50.
in 15. So I should be able continue down here. We're going to run free 15.
Fast bits. Yeah.
And so now it is in the fast bin. And 380 is in the small bins. What do I got to do now?
I don't think it's gonna.
You don't think it's going to work?
No.
I
If it consolidates within the fast bin, it's gonna do a 40 hex 40 chunks starting at 380. It's not starting at 380.
wait, which no, so the starting address of consolidation is whichever address is smaller, right? So 380, 380. 380 is the smaller address. So this will be the starting address if I get these two to consolidate. And they are eligible for consolidation because when we look at where they are located physically, they are in fact chunks that are physically located right next to each other. So it is possible for these two things to consolidate, right? The question is can we make this happen? Right? I think this is a fun little exercise.
What's the difference between they can and can we make them happen? Like, if they
So-
can, then we can make them happen. If they can consolidate, that means that we can't. Like, I'm confused.
In order to consolidate two chunks, the chunks must be right next to each other. Right. Both chunks must not be marked as in use. Now, the reason this gets a little bit confusing when I say a chunk is in use is we don't look at the flag for the specific chunk. This previous in use is for 380. The previous in use of 3C0 is determining that right now 3A0 is considered in use, right? This flag is determining the state of this chunk. Why is 3A0 still in use?
So we question.
Yeah, I know the answer. Sometimes I know the answer to the questions I ask. So the tcache was a caching layer, right? Everything in a tcache is a lie because even though it's been freed, it's marked as in use. Is the fast bin a lie? Yes.
Yeah.
The fast bin is a caching layer that is performance optimization. And in order for it to be a caching layer, everything that's in the caching layer, we just pretend that it's in use and we lie to the deeper parts of the heap because we don't want it to consolidate. So how do I make this chunk at 3A0 not be in the caching layer, right? Make it not be marked as in use, which is counterintuitive because you look at this, but when you think about the previous in use flags again, you want to look at where they are. So this flag says 3A0 is in use. This flag here. How do I change that flag?
Do the small bins not lie?
Do the small bins not lie? The small bins do not lie.
So if you move that 3A0 chunk into the small bins, then the next chunk's previous in use would be unset.
Okay, so if I could move this into the small bins, and the important thing isn't specifically that this goes to the small bins, right?
It's
It's
out
that
of the
it's that it gets out of the fast bins. You're correct about where it would go,
Yeah.
but if, for instance, this was something that would go elsewhere, we could apply the same logic. And how do I get something out of the fast bins? Big Malik, exactly. All right, I don't know what index I want.
I don't think we used
12? 12 sounds like a good number. All right. Well, Malik 12. What was our big number? 4096. It is a big number. Okay. What did we do?
the books.
We got rid of both of them.
They consolidated.
Okay, so what happened here? Well, we're looking for 380, right?
It's
Great.
it's the one we allocate. So we did do what we wanted to do. It just happened. So we didn't have to set the previous in use of the other one for this to happen.
Well, we did.
It just happened.
It just happened all in one big move. Is that the pointer that got returned then?
Yeah, 380.
Huh.
But
Right,
can you
so-
see those steps happening incrementally in GDB, or do we just like theorize and say it must have happened?
Okay, so for Twitch, I think Twitch can pick you up in this nice group that we have. But the statement is can I break those individual steps in GDB and see it move, for instance, from the fast bins to the unsorted bin, small bin, right? See those steps. The answer is yes, you can, but it's more pain than it's worth. One of the things that I try and do in the class is link to various pieces of glibc source code. Some of them apparently are wrong. That is clearly 237 when we are working on 235 in this class.
I think that links to why this needs to be 65 kilobyte.
Yeah, that's a shame. But you can break inside of, for instance, malloc.c, right? We could step into the implementation of malloc and see where these things get consolidated, right? Like the numbers that I have on the slides, I pulled them by staring at glibc source code, over some period of time, questioning my life decisions. And we can see how it does it. But what you would need to do if you wanted to see where is the point where consolidation is happening, like this right here, I don't know exactly where we are, but we see that we're looking, is the next chunk the top chunk? The top chunk is the wilderness. And so here it's saying, well, if that's the case, then we need to set the in-use bit and update this, right? And so you can kind of read this as far as, am I looking at the next chunk? Am I looking at the current chunk? One of the interesting things that you'll see if you start digging into this is the current chunk that you're dealing with is typically called victim. But fun fact, right? And so we see this logic. But if you wanted to step through it in GDB, you'd be stepping into this. This is pain.
Yeah.
All right. I had you guys step through file structs, right?
This is even worse.
This is way worse.
Um,
You'll definitely end up
seeing what you want to see.
you'll definitely end up seeing what you want to see, and you will end up at some point in this module throwing GDB on stuff and ending up in here. You won't end up here, okay? Just because you'll make a mistake. Where you'll end up has to do with this. This. When we start talking about, is that take a chunk off, unlink? Where's the check? Yeah, okay, it's there. Built-in expect. This right here. Where you'll end up, which is what we're going to try and touch on a little bit here, is when you start thinking about corrupting metadata of these chunks. Because the tcache, despite the fact that safe linking exists, is a pretty easy thing to corrupt, right? There's just a singly linked list. If there's a next pointer, and we just kind of go, right? Whatever we write. Well, it turns out the small bin and large bin, and I believe the unsorted bin as well.
They all have safe.
No.
Oh.
No. You actually are spared from safe linking in parts of this. And that's where this bins slide deck is useful. The singly linked lists that are similar to tcache have safe. All right. But if you get to the larger bins that are doubly linked lists, like the small bins is a doubly linked list, which means that there's a forward pointer and a backward pointer, or the unsorted bin is a doubly linked list, or the large bin, which is a doubly linked list, we don't have to deal with safe linking protecting these pointers. It's going to be great, right? Easy peasy, right? Those foolish heap developers. But it turns out that the heap at various points will verify your doubly linked list. How do you verify that the pointers are sane in the doubly linked list? Right? I want to remove a chunk, and it's a doubly linked list. Let's see if I got a good slide for that. Yeah, that works. It's a doubly linked list. For those that are unsure how to kind of parse this thing, your pointer of the allocation is going to start. This is, I would say, physically. I'm going to use physically again, but like based on virtual memory addresses, so it's somewhat valid. So like the allocation starts right here, which is where the forward pointer is, much like what we had with the tcache, where there's just the next pointer. Then instead of it being called next pointer, we call it the forward pointer. Now, instead of having a key, which is what we had in the tcache, then the next 8 bytes after the forward pointer is a back pointer. Now, these next forward next size and back next size, we're going to ignore for right now because they only matter for the large bit, which happens to be the graph that we're on. All right, but we're just thinking about a generally linked list, or doubly linked list. The forward pointers go forward, the backward pointers go back. So when we need to remove a chunk and return it to the user, there's some cleanup to be done, right? We have to set the forward pointer's back pointer to be my back pointer's forward pointer, and then the back pointer's forward pointer to be my I got that wrong. I got to set you yoink this out and connect the lines through, right?
Yeah.
I think it's just easier to say that, right? That makes sense. Right? We could pull this guy out, but we have to fix up this pointer and this pointer going forward and this pointer going back. Right? But there is a verification that occurs, like when we malloc and free things, that is just a sanity check. This says, if I go forward and then I go back, does that equal me? This is a check for corruption. So the safe linking, all right, that was a pain, but the heap didn't really check anything, right? It was the singly linked list. I could override a next pointer, and it's just like, yeah, man, whatever's there, that's what you get, right? When we're dealing with these doubly linked lists, if I'm trying to look at this, it's saying my forward pointers,
Backwards.
backwards pointer needs to be me.
But
So-
we fix it. It's not gonna be done.
Yeah, so if I just overwrite this forward pointer, it's going to point to, something I'm interested in, flag. What happens when it performs that check? The forward pointer, which points to flag, and then it is going to look at flag's backwards pointer.
God knows.
No, we can reason about what flag's backward pointer is. All right, we're clever. So we point to the allocation, right? So if the forward pointer points to flag, what is the forward pointer of flag? First 8 bytes of the flag.
The forward pointer of flag.
The forward pointer of flag. If we just pretend that flag is a chunk,
yeah,
right?
yeah.
Like what is this going to do when it does this check, right? If I just YOLO override flag or override a forward pointer of a chunk, of a free chunk to point to flag, what is this going to do? Forward would dereference to flag. Back would be what?
The next thing.
Right, the second 8 bytes, the second set of 8 bytes. Does that equal my address? That is this question.
Most
Right.
likely.
It clearly won't, but this is something that we need to think about because one of the things that is key to some of these challenges is creating a chunk from thin air. All right. And that means that we need to understand what this check is doing, right? Whatever the forward pointer is doing, that address plus 8 needs to be me. Similarly, whatever is my back pointer, the 8 bytes that are located there also need to point to me. Otherwise, I fail this check. And so when we start talking about corrupting the metadata here,
It's an or condition. It's not an and.
yeah, but this is also a not equals. We'd have to go
Oh.
to Morgan's on this. Right? It's like, if this is bad, then we say it's corrupted. Or if this is bad, we also say it's corrupted. All right, is the literal.
So the
law.
forward and the backward
Yeah.
have to be true.
Yeah, both of those must resolve to not resolve correctly to not explode. You will explode here. You will throw GDB at it, and you will find this amazing thing. It's part of learning the heap. But you know what? That's not all. Because what other metadata exists that we've messed around with in the tcache? We had the size before, right? Now, one of the things that in the tcache lectures we talk about is the previous size. And if I remember right, previous size isn't actually used in tcache. It's just one of these big misses, because we talk about heap metadata in the big sense, in the broad sense, but as far as what's actually used, previous size isn't really used in the tcache, but it is used over here in our doubly linked deep metadata implementation, because in the dynamic allocator misuse, one of the things that we might have done if you made it far enough in a challenge is we think about how things are located in memory. Let's say that I, for whatever reason, can write to this chunk, right, at the beginning of it, at the beginning of the allocation. I could fill this allocation and then overflow and start corrupting, for instance, the size value of the next chunk, right? Remember that was a cool trick. It let us create overlapping chunks and allocate things of sizes that weren't real. Well, let's see what the heap has to say about that. Well, what's that check right above me here? What is this guy doing?
That's the same thing, but with the size.
That's the same thing, but with the size. And so now what we're saying is, okay, well, is my size what the next chunk says is the previous size? And except this is resolving from the pointers, right? This is verifying the pointers. This is verifying when this says next chunk. What does that mean?
To see what next chunk.
Well, you could. We can. Let's do it. Boom. It is a macro. And it is this. So when we say, and then this is where like things can get a little bit convoluted when we start talking about what is like the next chunk or the forward chunk. I like they have a forward pointer now, and then a next chunk. Is this referring to pointers or is this referring to physical proximity?
By the comment.
Well, how about the code? How about we look at the code, right? We're literally looking at source code, and we still are unsure what's going on. It's a testament to the developers of the scene, right? So I have a macro that is next chunk of P, where P is the current allocation that I'm working with, or the current chunk I'm working with. We have some caching. I don't really care. It's a char star, so our addition is going to be 1 byte in size. What we are looking at here is the pointer of where I'm at plus the chunk size of me. So that means I'm just doing regular old pointer addition, and this is physical proximity, right? How do I know where the next chunk is? And this is what GDB is, or not necessarily GDB, but Jeff is, how does Jeff know where all these chunks are? It's using the metadata to surface this to us. When we start corrupting the metadata, Jeff is going to not be able to tell us what's going on here, right? If I were to overwrite the size value here, Jeff is going to just, I don't know, it's going to imagine that there's a next chunk way further out than it is, because Jeff is figuring out where these chunks are in physical proximity by taking some pointer, adding 20, I get the next one. Right, here's the pointer, I'm adding the size, I find the next one. Right, that's really all that's happening here when we talk about what is the next chunk. So let's pick a chunk. I want to find the pre size one. What do you got a favorite chunk? So someone's got to have a favorite chunk. One of these numbers look particularly friendly or scary.
The wilderness.
That is like the one exception here, right? It is technically a chunk, but let's go with this guy here. Easy to see. 98 4300, right? It has a size of hex 20. Where is the prev size for that?
Bytes before the address. 16 is the size in that previous.
Yeah, 16.
That's in the tcache.
This is in the tcache? Oh, okay. Am I baiting you with unintentionally baiting you?
It isn't.
Okay, let's avoid the tcache. What do I have here? I have something there at 5390. Okay. Where is the previous size for this guy? At 5390. Now, if we consult our representation here, we should be able to find it at the next chunk back a little. 16. Okay. The statement was next chunk minus 16. What was my beautiful chunk? 5390. Okay. My next chunk is this guy here. So let's examine, let's just print out a few in case we can't math. Not that. Examine 8 giant hex. 5390 is what we wanted, so it's this chunk. Come on. Examine 8 giant hex at this minus 16. Okay. And what do we see? 70B0, which is its size. And so what the size track is doing is it's verifying, well, with that this value is equal to 1. Where's the other value that it's comparing?
Size of the.
It's just size.
Its current size. Where was our lovely chunk? 5390?
Yep.
Where's the size of this located in memory?
8 bytes.
8 bytes.
8 bytes behind it. All right. Let's verify that. It's a good day when the computer does what we think. All right. Anyone that remembers why are these different?
Previous and use split.
Yes. So these are the same value for the purposes of the heap. The least significant. I want to say byte. That's right. The least significant bits of the size are how in memory these properties are set. And so we can ignore, for instance, a 1, 2, 3 right here. This is really just a side effect of how the heap is storing this information, these flags values. We're storing the least significant bits here because, especially now that we're on like a modern libc, malloc is always going to return me something that is a multiple of 16, which means that least significant nibble is absolutely useless from a size standpoint. Okay. So you see the kind of the enemy in front of you here, right? As far as what values need to be correct in order for this to not explode. If you have any questions about consolidation, any questions about these pointers? Okay.
When does this check happen? Like, when do you actually check for both of these things?
Good question. So when are these actually validated, right? When is the heap going to explode and yell at me? I don't recall off the top of my head, but if I look at my own source that I linked to, this is on unlinked chunk. Well, when we unlink a chunk is the act of taking the chunk out of the doubly linked list, right? So before I yoink anything out and actually return it, right? We would unlink something, for instance, when malloc is called. That's when the heap needs to unlink something from this representation and then return an allocation from the malloc call. That is before it yoinks it out of here and returns it to malloc. It's going to verify all of these pointers weren't messed up. So that makes it very difficult, right? To overwrite stuff. There's a lot of fixing up of memory to make all of these checks pass. And that is what this entire module is. There's various ways of messing up these pointers and moving things between these bins to ultimately get malloc to return you a pointer that you could leverage as an arbitrary read or an arbitrary write, right? Because if you think back to I'd say primitives when we were messing around with the tcache. What was the difference between getting an arbitrary read or an arbitrary write from the point of the heap? Do I need to do anything different with the heap if I want to read versus a write? Yeah, right? The trick for heap exploitation is to just get the heap to give me a pointer. Whether it's an arbitrary read or an arbitrary write depends on what I can call on that pointer, how I can use that pointer once I obtain. So that is all I had planned for the demo, which is nice because I did hit my 2-hour mark. Do you guys have anything that you want me to do on stream right now? Give a moment for Twitch in case they had anything. You saved me from the guard allocation, but you've been pretty quiet since. Because doing anything further than this would be trying to, for instance, create a fake chunk, which we can certainly do with our example that we have. We have enough to do it. But there's a lot of fixing up memory and reasoning about that. And I think part of the fun of this module is looking at a POC, reading it. Like this one isn't that long, right? It's only 48 lines. Most of it's like print comments, right? But what we see free the first fake chunk. Okay. So like maybe it's not that bad to create a fake chunk, right? There's an example of how to do it right here. And what the goal is that you can look at these POCs, determine what, again, maps to the requirements of the challenge, and then implement whatever this POC is telling. One of the weird things when you look at, and this isn't specific to how to heap, but it's true for just heap POCs in general, is they use this like weird syntax a lot for indexing and accessing memory. What is this?
Like 30 chunks.
Okay. So then, right, it's a void star, so it's just a pointer to whatever. This is an array of it. But what you'll find is they do a lot of indexing into pointers, because in C, a pointer and an array are fundamentally the same thing. And the thing to keep in mind when you're looking at some of this stuff is that what is the size of an index, right? If it's a void star, then the type is a pointer, so every access into the index is actually a multiple of 8. And so like, if I find, let's see if I can find one where they do this. That one's pretty straightforward. Particularly when you're talking about like next pointers and things like that, they will reference them as array indexes into a pointer, which can be a little. I just say this and then I can't find one. Okay, so and I don't know that this particular hawk is useful for the challenge, right? It's just an arbitrary thing that I grabbed here. But they're saying I want to create a big chunk in the stack. So they have this location, they're zeroing out the first 8 bytes, they're zeroing out the second 8 bytes, and then they are setting the third 8 bytes to be whatever this victim chunk is, right? And so this is actually a representation of a chunk, where this would be, for instance, your forward pointer, your back pointer, and then this would be the large forward next. All right. Twitch had nothing. So I think I'll just let you guys suffer for a week, right? Hopefully we'll come back with some questions. And that will drive the demo that we have next week. This is sufficient for you to get started. The first few levels, which I think I mentioned at the beginning, are just about leveraging consolidation. So it starts off with what we did at the beginning of the lecture here. We take a look at the challenge, very similar, because I ripped my example as a superpowered version of the challenges. Yeah, I can malloc something that's 200. Can I malloc something that's 8? Yeah. Can I malloc something that is 4096? No. Right. So there's some restriction on the size that you could malloc. And then read flag here is going to malloc some size that you cannot directly malloc. Right. And so we have to leverage consolidation in the unsorted bin, how we slice off a piece of the cake to get a use after free that can give us the flag. And then after the first 3, it's learn about some bins the hard way. All right, with that, I'll leave you all. Goodbye, good luck. I will hold office hours on Friday.